And this talk is basically 3 to 4 ROSCon talks rolled into one, so I'll go a little fast because I have to cover a lot of things. Yeah, I'll give a brief intro of the DRC, Team ViGIR. Are the mics okay?
Yeah.
Do you hear me?
Getting close, maybe a little bit closer and speak up.
Closer, okay. Then I'll briefly go over the infrastructure, what we did in terms of infrastructure using ROS. I'll provide a system overview about the open source software we provide now, go over the DRC finals results, and then talk a little bit about the lessons learned. So what is the DARPA Robotics Challenge? The DARPA Robotics Challenge is motivated by the Fukushima disaster. Yeah, the idea is that would we have had a robot that can go into this disaster and can manipulate valves or so, then much of this could have been averted. And that's DARPA's motivation for bringing this competition to life. And the idea is to use human tools, to have a human-shaped robot, because then you can operate in environments made for humans, and you can use tools made for humans. For instance, you could drive a car with your robot. This is the actual tasks of the DARPA Robotics Challenge. So you first start your robot in a car, drive down a course, then get out, go through a door, open a valve, drill a hole into a wall, stuff like that. And you also have some options. For example, you could decide to only walk and not drive, but then you would lose points. So yeah, what are the C's in DRC? The challenges in terms of locomotion, we have uneven terrain, stairs and ladders, motion with multiple contacts, for example, when getting out of a vehicle or getting up a ladder. We need perception. We need to perceive the environment to have robust locomotion. We need to perceive objects for performing manipulation. We need the ability to acquire new objects on the fly. And this is happening outside, so you have to be robust to outside lighting conditions. And we do manipulation. We did manipulation in the DRC, so there are different tools. Not all are not known in advance, so you have to on the fly adapt to the situation, basically, and with your robot. And all that you have to do under limited communication to a human operator. So you have to have a clever mix of autonomy and the cognitive capabilities of the operator playing into that for making this system really perform well. So the meta challenges are really highly compressed timeline because all this took place in less than 3 years. There were multiple competition events. There was a virtual robotics challenge. There were the trials and the finals, and for each of those you had to be ready. Then there's, of course, systems integration. You have a lot of components that have to come together and work. And, of course, you have to have high reliability because you only have a few attempts at these tasks in the competition. You can't try it 10 times and make a nice video. When it worked the 10th time, then you're done. So Team ViGIR is a mix of institutions. It's an international collaboration. We started out as Virginia, Germany Interdisciplinary Robotics, and the name stuck. First, Talk Robotics, a company from the US, TU Darmstadt, us, Virginia Tech, and then over the course of the project, Cornell University, Leibniz University, and Oregon State University joined us, working on different things. And what is relatively unique about our team is that we span 9 time zones, which of course also is a challenge because, yeah, you can't just run up to the other guy and, complain to him about something or so. Yeah, we're a Track B team. DSC participation from day one, so we wrote a proposal. We got funded for participation in the Virtual Robotics Challenge. We were among the best 6 teams, and for that reason got an Atlas robot. Then we participated in the trials and also in the finals. The software is available on GitHub. Nearly all software, with the exception of the robot controller, because that uses Boston Dynamics proprietary code and will not be useful to you guys. And also the communications bridge, because that is very custom made and has to be cleaned up a little before we let it loose. So let us know if you're interested in that. There's actually there were other teams using our software at the DRC finals. Team Hector from TU Darmstadt, which is kind of a spin-off of my group. We decided very late to also get an entry with our Tormeng robot. and Team Valor from the track group at Virginia Tech. There's also open source efforts by other competitors, so we are not claiming we are the only ones. And MIT did a lot of very cool stuff, like the Pronto State Estimator, the Drake Planning and Control Framework using MATLAB, and also now C++. It's a very comprehensive system, very cool. They also have their user interface online, so that's certainly something to look at. Then IHMC, of course, who scored the second place at the DRC finals. They have published their code as, they have published their simulator and their controller, but in binary form. But I talked to them and they want to do the full open source release this fall. And yeah, I say this here to encourage them to actually go through with it. So. Yeah, and the University of Tokyo also has extensive ROS-based software online. I haven't seen them talking much about it, but I wanted to state it here because it looks very useful after I briefly looked over it. So hardware, we use the Boston Dynamics Atlas robot, hydraulically actuated. Our Atlas is nicknamed Florian after the patron saint of firefighters, very much in line with the whole topic of the DARPA Robotics Challenge, disaster response. There's an API provided by Boston Dynamics that allows the robot to perform walking and stepping motions and balancing, and teams could use that, or they could decide to roll their own controllers. And if you use it, you have to some extent, decoupling of upper body motion from low-level balance control, of course. So there's actually not the Atlas robot, there's multiple Atlas robots. There's Atlas V3 that was in use till November 2014. That one was tethered. You see the tether back there. It had 6 DOF arms with pretty bad kinematics because of the way they were mounted. Everybody was complaining about that. So with Atlas V4, that actually got a battery in the back now. They also changed the arm configuration for much better manipulability. And this machine also has 3 Core i7 computers on board for onboard computing because it's operating completely untethered. And this one still has the 6 DOF arms because the 7 DOF arms in the final Atlas version came a little bit later. And and you can tell because these are the silvery thingies, the last 3 joints are electric driven. Yeah, so infrastructure. We used ROS from the beginning because we had a lot of prior experience with it. Great community, obviously. Not many robotics frameworks can claim filling a room like this. Yeah, a lot of useful software, of course, and integration with DRC Sim was also, of course, it was kind of a no-brainer to use ROS. Our development, happened in private GitLab repos, but now basically everything, with very few exceptions, moved to GitHub. And as I said, we are operating over 9 time zones, so we use Redmine a lot for coordinating the whole project, everything in tickets and hundreds of wiki pages for explaining how things work. Yeah, a little different timeline with a focus on infrastructure. So I have here the Atlas versions, and the Ubuntu versions, and the ROS versions, and ROS build and Catkin. And there's a few things that are interesting. So one thing is that actually the newest Atlas version came pretty late for the teams, and that was something that every Atlas team had to cope with. Pretty late, we had this additional degrees of freedom and had to adjust to that. So that was more on the technical side. Yeah, we actually. Okay, should I take a...
Sorry, can we get this mic live?
Yeah, it's probably not a good idea to turn the head.
Yeah. I think they're having trouble hearing you in the back.
Okay. Okay, I'll go on so we don't lose too much time while the mic is prepared. So actually we used Fuerte and Groovy at the same time. We used Fuerte solely for DRC Sim and then Groovy for everything else because we wanted to use the newest.
There you go.
Oh, perfect.
Get better
Okay, does it work? Yeah. Okay, so we used essentially Fuerte only for DRC Sim and Groovy for our workspace. So that works in case anybody's wondering. It's not super convenient, but it can work. Yeah, the other thing that was mildly annoying was, and I talked to Dirk already about it, is the switch from Hydro to Indigo and simultaneously being forced to switch from one Ubuntu version to the other, because then you have to redeploy all your computers and stuff, and that was kind of annoying. I'm not sure that can be done better, but maybe point for discussion. And the other thing is we started out using ROSbuild, and then it took a long time to get rid of ROSbuild, so that was also fairly annoying, but things got much better once we finally got rid of it, but it took quite some time. Yeah, some more points about infrastructure. So with our humanoid robot and our Atlas versions, it was kind of hard to manage the variability we had. We had 3+ robot versions, we had 4 hand types. Yeah, you can do something with arguments and parameters and launch files. It's kind of unwieldy to forward that stuff everywhere. So we used environment variables. It's something you can do. I'm not saying it's the best approach. And we generate the robot model and onboard software setup at launch time. So this is an excerpt from our Atlas model, and you see all these environment variables here, and that's basically how we decide which Atlas we instantiate and which hand we instantiate and so on. And yeah. And we also implemented a deployment infrastructure because we didn't find any that satisfied our requirements. I am glad to be proven wrong there. So we have a complex system. We have 3 onboard computers. We have 1 field computer. We have 4 operator control station computers. We have fast development cycles. You want to build and then deploy it everywhere. And for that we did some bash scripting and remote launch scripts that build using Catkin, do a Catkin install step, deploy using rsync, and then start stuff using SSH and screen. And this is basically a folder with a remote launch setup, and then you have per machine, you have a launch script, and then you have an environment setup where you, for example, can set these robot type variables, because that's the thing that you need to do if you use this environment setup approach. Another word about infrastructure, simulation options, because if you guys want to try stuff, you probably want to simulate a robot. You can't buy an Atlas at the next convenience store, I heard. So, but you can actually download it for free. So the options are limited right now, because if you want to simulate Atlas, you have to have the BDI interface, but only DSC competitors have that, so you can't really walk. That's not so good. With the HMC controller and simulator, you can walk, but you can't do manipulation. But with the upcoming HMC release, you will be able to actually do both. And what we provide already is simulation of our Tormeng robot in Gazebo 4 and being able to do manipulation. Yeah. So now I'm going to talk a little bit about the different components. This is a little bit simplistic, but putting a giant flowchart on there is probably also not the best idea. So let's start with the hardware and specifically the robot controller. So we decided to use the BDI supplied behavior library because we are not whole body control and walking experts, unlike IHMC and MIT, for example. And for that reason, we use the BDI supplied library, walking, stepping, manipulating. This is provided as a binary, as a black box, no source code, also for DRC teams. So you kind of have to take what you get. And of course, I mean, Boston Dynamics was very helpful. Every time we had an issue, they would respond. But it's still not the same thing as having source code. And of course, it's not available to the general public. But as I said, we are working on integrating the HMC whole body controller. And we actually worked on integrating it for the competition, but time constraints just didn't allow for it. Next up, what you need is state estimation for your robot. You want to pose estimate for your robot, and with these big humanoids that have pretty good sensing, you can fuse slack kinematics and IMU data and get a continuous but low drifting state estimate. And we use MIT's Pronto system for that. It's very well tuned for the Atlas system, but it uses the pod build system from MIT and also the LCM communication system. So we had to do some plumbing, interfacing these two worlds. And we didn't actually use the LiDAR functionality because it's kind of dangerous in non-static environments. Because in the DRC final, somebody could walk around and then suddenly your robot thinks it moved because somebody in the environment moved. So we didn't do that. Next up is perception. So we did quite a few things there. What you want is you want to provide situational awareness to the operators over the constrained link. You can't just send the 100 megabytes per second of data you get from your sensors. And you want to provide a world state estimate for the robot, because based on that you do collision avoidance, both for footstep planning and manipulation. Yeah, we implement our own Octomap updater that is a little bit different from the standard one that's coming with MoveIt. It's also updating the onboard environment map in real time. It provides a collision model for the planner, and it provides filtered LiDAR data for the whole system. That's a little bit different from what the standard one does, because we annotate the LiDAR data with transform information, and then we can send it over the wire and reproduce the whole point cloud basically on the operator control station side. Yeah, and because of our constrained communication link, we could only send standard UDP packets. We compress the LiDAR scans, we split it into 3, and then discretize the distances and the intensities. And what we also transmit is a bit that tells us if the LiDAR point is part of the robot or not, because we want to have that on the operator station also to have filtered data. For example, not the robot arm in the operator station. Yeah, and we also add start and end global transform info, so we can perfectly reproduce the scan. Yeah, then we have a world model server node that collects the LiDAR data and provides services to other nodes like point cloud regions of interest, Octomap regions of interest, grid maps, and distance queries. And there are 2 instances running actually. One is onboard, the other is on the OCS side, and they are synced via this compressed scan approach. Yeah, the other thing we looked into, but we didn't really end up using in the finals, is using fisheye cameras. The fisheye cameras, the situational awareness cameras on the robot, the images from those are kind of hard to interpret for humans, so we calibrated the camera using the OCamLib toolbox, and now can basically create virtual pinhole cameras that follow TF frames. That was useful and available online, so if anybody's interested in that, you can use that. The other pretty cool thing is mesh visualization in RViz. So yeah, we generate mesh data either from depth images or from LiDAR data. And then we also take an RGB image, and then we texture map that in RViz texture map the mesh in RViz in real time using augur function calls. And that actually works pretty well. And yeah, on the left here you see the RGB and the depth image, and on the right you see 3 of these novel views just in RViz rotated around and stuff. So that's all also available. Yeah, next up is footstep planning. This is actually based on the work by Armin Hornung, but very extensively extended. Yeah, complex locomotion, we have to do 3D perception, we have to do safe sequences of foot placements with 60 degrees of freedom, obstacle avoidance, for example, when going through a door, and of course have to observe balance constraints of our robot. We took a divide and conquer approach for that, and just decoupled the terrain model generation from the 3D footstep planning and obviously the robot controller. So yeah, the terrain model generator is using an Octree as a backend, does incremental updates, and also available as a standalone ROS package. Linked, yeah, by the way, so there are always links on the slides, and when you have the PDF, you can click on them, and then you go there. And that's how this updater looks like. So you have the spinning LiDAR, and you see how the normal estimates are updated, and also the height map is updated in real time. Yeah, originally this footstep planning approach was only 2D capable, so it was extended to 3D. The states become full 60OF, but the actions the robot can perform remain the same because the roll, pitch, and step height are constrained by the underlying terrain. So the search space doesn't enlarge. and that makes planning not as slow as it could be. And what we also do is ground contact estimation, so we estimate where the contact between the foot and the ground is, and this allows to also plan with overhanging steps to some extent. And the footstep planner is very customizable. There's a lot of inflection points where you can drop in plugins to make your robot work with it. And we already have 3 setups basically, one for Atlas, one for Tormang, and one for the Azure robot from VT. And this is the footstep planner in action at the trials. This shows going over the chevron hurdle. And you can see that the robot's actually doing this overlapping step, the step 4 that's coming up. That's actually overlapping the chevron hurdle quite a bit. Now it's placing the right foot there, and you can see that it's actually, and crossing that with Atlas is really only possible when you do that, when you consider that, because otherwise you can't get any footholds. Yeah, the other thing that's supported by the footstep planner and the operator control station is interactivity, so you can drag the goal and create a footstep plan. And then you can modify single steps. If the operator thinks that something's wrong with this one step, then you can edit it, and other steps also will indicate if they are still safe based on what one did to the other one. Yeah, the next big thing, of course, is manipulation. Yeah, what do we need? We need collision-free planning. We need the capability to do Cartesian motions, because, for example, for drilling a hole in the wall. There's a lot of manipulation in contact with the environment. And of course, at the same time, the robot should always maintain stability. And what we want is to be able to have sliding autonomy. So we want to basically be able to do teleop if things go wrong, but we also want to be able to, in the middle ground, have like an object-based approach that's based on object templates, and also the ability to just go fully autonomous if things work correctly. And we decided to use MoveIt as a backend because it largely satisfies these requirements. Yeah, the same thing as talked before. There are different robot variants, and we actually used Xacro also for the MoveIt config. So I don't know if people do that, but it works to some extent. And you can actually also set up the collision disabling stuff to work. Yeah, that's the motion planning overview. We basically have additional plugins in Move Group that do our own special stuff. And the main thing is our ViGIR Move Group action that extends the standard MoveIt action goal to also support Cartesian goals, Cartesian path waypoints, and circular motions. And also specifying a reference point relative to the end effector, because when you drill, if you want to drill a hole in the wall, you want to do this with a reference frame, the drill bit as a reference frame, basically. Yeah, then we have an object template approach that's built on top of this additional ViGIR Move Group action. The operator places templates, objects in the environment, and then planning happens relative to these instantiated objects. And the object templates incorporate geometry, mass, inertia, graphs, and stand poses. So you place an object somewhere, and then you immediately can send your robot there. The other thing that we also developed is this ghost robot that is somewhat similar to what the MoveIt demo or Arvis plugin provides, but it has some additional capabilities. You can snap the end effector to objects. So you can say snap to this drill, and then your robot will automatically snap to that. And if you move your robot around, it will still keep the hand there. Yeah, you can move the ghost robot to stand poses relative to object templates. You can selectively constrain joint limits. Yeah, and based on the ghost robot, you can send low bandwidth planning requests directly from the OCS. So in the ideal world, this works like that. You have an object, you have your robot, you get a point cloud of your object, you put your object template into the scene, then you can click send ghost to object, then your ghost robot will be sent there. Then you can play around with things, and if you're satisfied, you tell the system it should send a footstep plan, and then off you go. So this is an example of the planning system doing an assistive motion with a paint roller. So we can't reach the valve, and so we use this paint roller, for example, and this is actually using this object template approach. There's a valve template and a paint roller template, and we use that in conjunction with our Cartesian motion setup to actually turn that. Now, where MoveIt has a certain weakness is whole body motion. So what we did is we developed a bridge to the MIT Drake framework that allows planning whole body motions, and by just switching out the desired planner string in our planning request, we can switch to using Drake for planning. And this is shown here. This is full body inverse kinematics with the Tormang robot and picking up a pipe, interconnecting the ROS MoveIt world to the Drake MATLAB world, basically. Yeah, then the next thing we want to do is we want to also be able to do autonomy. So on the one hand, we have communication constraints, we have limited time, we have a complex robot system, so we want to go autonomous. But on the other hand, we have unstructured environments, we have complex tasks, and we need to be robust. So that really it's a good reason to have more operator support. And what we want to do is have this flexible collaboration between robot and operator. So existing behavior executives are really mainly meant for pure autonomy. So it's you start the thing and then it runs and that's it. But we want multiple degrees of autonomy. We want to adapt to unforeseen situations. And we want to be able to quickly set up these behaviors. So we developed this flexible behavior engine, and the main developer is actually here, Philipp Schillinger. He also has a Team ViGIR t-shirt. He's back there. So if you have detailed questions, you can also ask him. It's based on Smash. It adds robot-operator collaboration and a very sophisticated user interface. And so a FlexBE state interfaces the basic robot capabilities, and how that works is essentially you have this on enter, and there you send your action-lib goal, for example. Then in the execute, you check for the result, and then based on that, determine the outcome of your state. And then depending on that, you end up in another state. And then there's an autonomy level, so you can basically, during behavior design, specify how much you trust the different parts of the system, and then during runtime you can decide, if the situation is pretty clear and there's nothing wrong happening, you can go full autonomy, but if you see, this looks fishy, so I go to low autonomy, and then your robot will start asking much more, should I do this, should I do this, should I do that? And then this way you can flexibly adjust to the situation. There's also a mechanism for data input over the OCS, so the behavior can ask the operator for data, and this is actually integrated with the operator control station. For example, the behavior can ask for pose of an object, and then there will be a pop-up in the operator control station, and then the operator can provide that data. There's also the capability to do runtime changes, so you can actually lock the behavior during runtime, and then you can do modifications to the non-locked part, and then re-upload the modified behavior, press play, and then the modified behavior is run. So you can do stuff, yeah, whatever. You can really adapt the state machine on the fly also. There's, like I said, an extensive user interface that makes it very easy to develop behaviors because it's basically drag and drop. You have the different states, you can drag them in. And based on that, Smash code is automatically generated. So, yeah, it's a fully graphical user interface. Yeah, here's some screenshots of that. So you see these different states, and then you can copy parts and put them into another part of the state machine. That's all possible. It's, the user interface is actually a Chrome app. So that's how the runtime control looks like. You have the current state in the middle, and then you have the possible outcomes going to the right, and you can click on these outcomes. Or you can let the system do that automatically. I have a video about this in a non-DRC application, but I'm going to skip that and suggest you look that up online after the talk for time reasons. The next thing you have to do is we have to communicate with our operator control station, and that's done via our comms bridge approach. Because of all the communication constraints, it's of course unfeasible to use a single ROS master. So because of the unreliable connection, so we use a dual master approach, one on the OCS side and one on the onboard side. The data going over the comms bridge is prioritized, so a planning request has more priority, of course, than state data that comes regularly anyways. High-rate state data is treated specially because we compress it a lot because we know the joins only have this range, and then we really use all these details to compress it. Other data, generic data, is compressed using the blob tools package that basically does BZ2 compression by default. Yeah, and then we of course have an operator control station that you can see in some videos also. This is based on libarvis. We have 3 views that are separate processes. One map view top down, there you can actually do a rectangle selection and get region of interest data, octomaps, point clouds, grid maps. We have a main view that is used for manipulation tests, basically, or for star planning, standard, and a camera view for camera visualization, where you can also easily, for example, change alpha values for this augmented reality field that you also get with the Iris camera display. And then we have multiple Qt widgets for general controls, like a ghost control for our ghost robot and a widget for pre-canned joint configurations and things like that. So there are instructions for complete setups online. You can, right now, like I said, not get a full Atlas example, but you can at least get a Tormeng example that's for manipulation. I have a video here. I think I'm going to play that during the questions. So the other thing that's in work in progress right now is behavior synthesis, building on top of the FlexBE behavior engine approach. This is done by the guys at Cornell. Here we use linear temporal logic to generate behaviors on the fly, basically. You specify high-level goal, and then the system figures out the state machine to fulfill that goal automatically. And it's treating the outcomes of actions as adversarial, because then you're basically guaranteed that you specify this formal LTL specification. And yeah, this is probably hard to read, but this is, for example, a state machine generated for picking up an object from standing, looking down, aligning the object template, going into manipulate mode, and then picking up. This is, of course, a relatively simple toy example, but this is also work in progress, of course. Yeah, we also have a video of that. So this is not so long, so maybe you can quickly watch it. Specify the goal state, then this behavior is automatically generated. And then you just click on start execution and your Atlas robot starts looking down. And yeah, the operator aligns this template. So we don't have automatic template alignment. That's really a shortcoming because we figured that we want to be as robust as possible, and in these outside lighting conditions, you never know, so we always let the operator do that. And yeah, so that's the big eye picking up this drill. Yeah, so what happened at the DRC finals? We decided not to do egress because it would be a very significant development effort that would be a lot different from everything else we would do, and also risk catastrophic damage to the robot. And the other thing we did that would come to haunt us later is limited testing under the degraded comms conditions because we didn't have the exact same network emulator that DARPA provided. So what happened? First day, we are back there with in this car, our robot, our Atlas, Florian, and we slowly drive over the finish line, so that's good. Then we get a penalty because we don't do egress, like I said, so it gets pulled out, and then you get a 10-minute penalty basically. But then we go on, and then we actually had a comms issue. We couldn't send longer footstep plans, and we couldn't use the behavior engine properly in this run. So that was really bad. And for that reason, we had to switch to manual mode. And everything worked, but it was relatively slow. So yeah, now the door's open, and now Atlas has to go through there. This is actually pretty hard because Atlas is such a big robot. It's barely fitting through this door frame. So don't want to screw that up. Yeah, and next we go for the valve. Yeah, and here you really see that we couldn't do proper footstep planning because we always just did little primitive commands, and that really took a little time. So now turning the valve, that worked well. Yeah, and now we are not going for the wall task because it's much more risky. We are going for the surprise task that is hard to see here. And what you actually see is that the right wrist also gets out at some point. Yeah, now. That was the wrist mode not working. Yeah, and then 60 minutes were over, so where did the time go? Yeah. So we had flawless driving, we had a comms switch issue. We switched to teleop mode basically. It worked, but it was slow, of course. So day 2, we figured, well, let's try driving a little faster. And yeah, that was a little too fast. So. Yeah, I mean, it's probably a mix of communications problems and the intention to drive a little faster. So yeah, we had to call a reset. And then we drove again, and this time it worked. So yeah, that was a little bumpy, but yeah, and then disaster struck basically. So we opened the door, everything was fine, and then wait for it. Yeah, the pump shut down. So we don't know why, but the pump shut down. We had an issue at the beginning of the run where the arm wouldn't work, and we had the robot out in the sun for like 30 minutes before we could actually start. So we suspect that it might got too warm. We don't know. We probably will never know, but this was bad. So We tried again, picking the robot up. Second try going through the door, but yeah, it probably was damaged somehow. Yeah, I mean, we went through the door, but yeah. So, yeah, so that definitely day 2 wasn't our day. Yeah, the results, 3 points. I'm actually not sure which place we are in, but that definitely was lower than we expected, unfortunately. We could have achieved 7 points because we decided not to do egress. So, and the top 3 teams all scored 8 points, so we couldn't have won anyway. So that's like good. Yeah, we missed the chance at day 1 due to the comms issue, and the day 2 thing is probably a hardware issue that just haunted us. So the good thing was our driving approach worked really well on both robots that used it. So we also used that driving approach on the Tor robot, and the Tor robot actually was faster. That was good. Yeah, still a little bit of a bummer, the end result, but yeah. The whole DRC experience was really fantastic, and all the teams were, I mean, everybody was collaborating. We were leasing our Polaris Ranger vehicle to others, and vice versa. You didn't feel like adversaries. It was more like teamwork and yeah, going against this scenario and showing what robotics is capable of, basically. Yeah, some lessons learned regarding ROS. Workspace setup using WS2 generally worked well for us. Yeah, we have some convenience scripts that turned out to be helpful. Yeah, keeping pace, I talked about that already, from Roswell to Catkin and Hydro to Indigo. That's something we didn't like, but you can't, I mean, that's happening in every system, basically, to some extent. Using plain Catkin make with a large project is a bad idea. We actually used that for much too long, and Catkin tools is so much better. So I would really recommend everybody to use Catkin tools. Yeah, of course, we saw the limited communications capability of ROS, but I hear with ROS 2 everything will be awesome, so cool. Yeah, and supporting different configurations of robots feels more involved than it should, I think. I don't know if our environment variable approach is the right one, or if people have other ideas. I don't know. Yeah. Some big picture lessons learned. Yeah, having a transatlantic 9 time zone team actually can work with the right mindset and people and tools, of course. Yeah, the DRC showed what is possible, and it was really a brilliant display of the state of the art, but it also showed that there's a long way to go till robots can be useful for real tasks like that. Everything was really slow still, not only for us, but even for the top teams. Yeah. The other thing I didn't talk about is continuous integration. We didn't really do much of that, and that's really bad. So we're really interested in getting simulation in the loop testing and so on working. Because for projects like this, it's very important to have the full system, because it often breaks at the seams between components. Yeah, in the end, I think everybody wins, because a giant leap with over a wide range of capabilities was shown in the DRC. There has been a lot of open source developments, Gazebo, Teams, open source releases, and yeah, like I talked about, the incredible sportsmanship and cooperation in the DRC was really great. So overall, that was really a great experience, great 3 years. Yeah. So that's what I talked about, and I'm nearly on time, so thank you.
Down there?
So in the last presentation, one of the questions that was brought out is sort of are robots going to continue to look humanoid, or are they kind of shift to look towards what their function is? After going through kind of your robotic challenge, do you think it's about having something that has a kind of human body to it? Was there like maybe another robot that sort of function better?
Okay, so let me repeat the question. The question is if anthropomorphic robots are like the way to go, or others, right? So I mean, the DRC showed that there's a lot of promise in all this, but these robots are super expensive and they are not really reliable. So I think it's good to see what is possible, but I see like small track vehicles to be much closer to a real application, obviously, because they are already in the real application, just not as autonomous as we might want them to be. Of course, if you have a humanoid robot that is as capable as a human, then that would be preferable. But we're on the way, but we are only here, and we have to go there. So. By the way, the video back there, that's the tutorial. You can download that and try it on your own computer. So.
Another question?
Yeah, so after going through this experience, what would you do different now? You had to do it again.
That's, I mean, hindsight is 2020, so I mean, you can talk all you want about what you would have done better. I mean, maybe, for example, this continuous integration example is something that really would have benefited from that. Yeah, I don't know. It's hard to say, really, because afterwards you're always wiser. But, yeah.
All right, last question up here.
So the question is if we had found some problems with real-time and ROS. So actually, I mean, you can make ROS real-time with oracles and stuff. So, but the thing is, the low-level controller on Atlas is actually running on a QNX real-time system, and we send it desired values, and then the low-level loop is closed on the QNX hard real-time system. So we didn't really have that problem to some extent. Yeah. But we used a real-time preempt kernel and spread priorities and some hoops to, I mean, there are these special subscribers and stuff, right? Publishers, real-time publishers and subscribers. We used those also.
All right. Thank you, Stefan.
Yep. Thank you.